Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to visualize the solar system right now. Specifically, picture the orbit of Jupiter. It is this massive, sweeping boundary far out from our sun, hundreds of millions of miles into the freezing dark. Now, instead of the cold, empty vacuum of space with just a few scattered gas giants and asteroids floating around, I want you to imagine cramming 4 entire blazing stars into that exact same boundary.
It sounds like a thought experiment designed to deliberately break the laws of physics, or, maybe the climax of a really intense science fiction novel.
Right.
But this is the reality of a newly observed, highly compact quadruple star system known as TESS 120362137. It is not a hypothetical scenario at all. It is a meticulously documented cosmic structure.
The sheer scale and density of this system are staggering. We're talking about the most compact quadruple star system ever observed to date. And we aren't just bringing this up because it's a neat piece of cosmic trivia. Understanding this tightly packed, chaotic system actually sheds light on some of the biggest questions in astrophysics. Things like star formation, the intricate gravitational dynamics of the universe, and how these exotic stellar objects evolve over billions of years.
Yeah, and it really changes your perspective.
It does. Whenever you look up at the night sky, you see what looks like a serene, quiet blanket of single, isolated points of light. But the reality is that when you are staring at one of those tiny dots, you might actually be looking at an incredibly complex multi-star dance playing out millions of light years away.
What is genuinely fascinating here is how a system like TIC 120362137 completely subverts our everyday intuition about how planetary and stellar systems operate. You and I and everyone listening are inherently biased by our own solar model.
Oh, absolutely. We have one dominant central star.
Right. We have tiny rocky planets close in, gaseous bodies further out, all sitting in orderly, widely spaced, predictable orbits. It feels safe.
Predictable being the key word there.
Yes. But the universe is incredibly diverse, and in many ways, our isolated, quiet little sun might be the exception rather than the rule. When we look at this new quadruple system, we have to entirely recalibrate our understanding of celestial architecture. To really grasp what is happening here, we have to look at the specific hierarchy of this system.
Because not all multi-star systems are built the same way, are they?
Not at all.
The architecture of this particular cosmic dance is what astronomers classify as a 3+1 type quadruple star system. To make that a bit more concrete, imagine a grand ballroom.
Okay.
If we were talking about quadruple systems, a lot of the ones we know about are what you would call a 2+2 type system.
Right, the binary pairs.
Exactly. That's like having 2 separate couples dancing the waltz on completely opposite sides of the ballroom. They are aware of each other. They are slowly revolving around the very center of the room, but they have plenty of space.
They aren't stepping on each other's toes.
That is a 2+2. This system, however, the 3+1, is entirely different. Imagine a tight trio of dancers in the very center of the floor, locked together in an incredibly fast, intricate salsa, while a single soloist dances a slow, wide circle all the way around them.
It paints a chaotic picture.
It does. Both setups are hierarchical systems, meaning they have layers of orbits nested within each other. But the 3+1 feels like it should be absolute chaos.
It absolutely does. And from a gravitational standpoint, it is a remarkably rare beast.
Yeah.
To put it into perspective, smaller 2-star systems, binary systems, are the overwhelming norm when it comes to multiple star systems in our universe.
They are everywhere.
They really are.
Yeah.
2 masses orbiting a common center of gravity is a highly stable configuration. When you move up to 4 stars, that 2+2 configuration you mentioned is much more common, precisely because it allows for wider, more stable gravitational separations. The math works out neatly.
So the 3+1 is the outlier.
A huge outlier. Before the discovery of TESS 120362137, only 2 other 3+1 type systems had ever been observed by astronomers.
Wait, only 2? In the entire history of astronomy?
Only 2 definitively confirmed 3+1 architectures, yes.
That is wild.
And here is the crucial distinction regarding those previous 2. Both of them were far, far less compact than this new one. They were spread out over much larger cosmic distances, giving the gravitational forces room to breathe, so to speak.
So TQEC 120362137 has essentially taken this already exceedingly rare architectural setup and compressed it into a space that completely boggles the mind.
Yes, it is unprecedented.
Let's map out those distances and sizes for everyone listening, because this is where the visualization gets truly wild.
Let's do it.
As we said at the start, the entire four-star setup, all four massive burning bodies, fits entirely inside the distance from our sun to Jupiter. That is roughly 480 million miles.
Which sounds like a lot to a human driving a car.
Right, but for 4 stars, that is basically sharing a sleeping bag. But it gets even crazier than that. That inner trio, the 3 stars doing the rapid salsa dance in the center, that entire inner subsystem fits entirely within an area the size of Mercury's orbit.
It's almost hard to comprehend.
Hold on. Mercury is basically scraping the paint off our sun. It is only about 36 million miles away from the solar surface. You're telling me 3 massive stars fit in that exact same gap. How are they not ripping each other to shreds with gravity?
It is a profound balancing act of orbital mechanics, and to understand how they survive, you have to look at the physical properties of those 3 inner stars. They aren't just tiny red dwarfs, which are the most common, smallest stars in the galaxy.
Right.
These 3 inner stars are massive, and they run significantly hotter than our own sun, though they do vary in their specific heat and mass. The undisputed heavyweight of this entire group is the primary star of the innermost binary pair. Astronomers designate this specific star as star A.
Sorry, got it.
It anchors the entire frenetic inner core of the system with its immense gravity and its intense thermal output. It is the gravitational linchpin keeping the inner trio from flying apart or instantly collapsing inward.
So you have this terrifying, blazing heavyweight, star A, locked in a tight embrace with a second star, and then a third star buzzing around that central pair like an angry hornet.
Exactly.
All within the space of Mercury's orbit. And then you have the fourth star, the soloist out on the edge. Tell me about that one, because from what I understand, it is drastically different from the inner 3.
It is. The outer star is much smaller than the chaotic trio it orbits. In fact, it is quite a bit like looking in a mirror for us, because that fourth star mirrors our own sun very closely in both its physical size and its surface temperature.
Wow.
Yeah, it is a G-type main sequence star, just like ours.
It's like having a replica of our sun just casually strolling around the outside of a triple star bonfire.
Exactly. And the contrast in their physical makeup is perfectly reflected in the rhythms of their orbits. The gravitational forces at play inside Mercury's orbital distance are intense.
Because they're so close together.
Yes. Because they are so close together and because their masses are so significant, those inner stars have to move incredibly fast to maintain their orbits and avoid falling into one another.
It is basic orbital mechanics, right? The closer you are to a massive body, the faster you must travel to maintain centrifugal balance against the pull of gravity.
You nailed it. Their orbital periods, meaning the time it takes for them to complete a single revolution around their shared center of mass, range from just a few days for the innermost pair to 51 days for the third star circling them.
A 51-day year. You would have to celebrate your birthday every other month while trying not to be incinerated by 3 suns. It would be absolute visual chaos.
Visual and gravitational chaos, yes.
Yeah.
And meanwhile, that outer sun-like star takes a much more leisurely pace. Because it sits further out near that Jupiter boundary we discussed, it experiences a much weaker gravitational pull from the inner trio. Therefore, it completes its orbit around the inner core every 1,046 days.
So you have this frantic, high-speed, high-heat blender of gravity in the center, surrounded by a slow, relatively cold, 3-year-long patrol on the outside.
That sums it up perfectly.
Which naturally makes me wonder, if a system like this is so massive, so dynamic, and burning so incredibly bright, why haven't we seen more of them? You said there were only 2 others ever found. Are they just that rare, or are we just bad at looking for them?
The astronomers studying this system have made a very crucial point regarding this exact question. It is highly likely that there are actually many other compact 3+1 quadruple systems out there in the galaxy.
Really?
Yes. The universe is incredibly vast, containing hundreds of billions of stars in the Milky Way alone, but finding them is fundamentally difficult. It isn't just a matter of building a bigger telescope and pointing it at the right patch of sky.
Either they just look like one dot.
Right. Their discovery relies on highly occasional and what the researchers call fortuitous properties.
Fortuitous properties, meaning we have to get incredibly lucky. It's essentially looking for a needle in a photometric haystack.
Right. That is a great way to put it.
Because when you look through a telescope, you don't just see 4 distinct, beautiful little dots circling each other. You just see a blur. So how did they actually catch TTIPS 120362137 What was the lucky break?
The lucky break was a combination of the system's sheer brightness and a very specific geometric alignment relative to Earth.
Okay.
The details of this discovery were recently published by Tomas Borkovits and his colleagues in Nature Communications. Because the system is unusually bright, it allowed astronomers to use a powerful combination of both photometric and spectroscopic observations.
But they had to know where to look first.
Yes. To even know they needed to look at it, they had to catch it in transit.
Okay. Unpack that for me. Transit. We were talking about shadows, essentially.
Essentially, yes. This is where photometry comes in. Photometry is the measurement of light intensity over time. We cannot physically resolve the individual stars visually. They are too far away.
Right.
They blur into a single point of light. But if the orbital plane of those stars is aligned almost perfectly edge-on with our line of sight from Earth, the stars will pass in front of one another from our perspective.
Okay, I see where this is going.
When a star passes in front of another, it blocks a tiny fraction of the light. We see this as a microscopic dip in the overall brightness of that single point of light. That is a transit.
So a light curve is basically like watching a car's headlights from a mile away and trying to figure out if a moth or a bird just flew in front of the bulb based entirely on a fraction of a percent drop in the brightness.
That is a phenomenal analogy, yes.
Yeah.
You are looking for a fraction of a percent of a dip in brightness, and you are plotting those dips on a graph over time. That graph is a light curve.
That sounds incredibly tedious.
It is. And ground-based observation alone wasn't enough to untangle a system this complex. They had to rely on initial data from space, specifically the Transiting Exoplanet Survey Satellite, or TESS.
I've heard of TESS. It's the planet hunter. What does TESS actually do? Just take really big pictures of the sky?
Not pictures in the way we think of them. TESS is designed to stare at massive swaths of the sky for weeks at a time and do exactly what we just described, watch for those tiny blips in light.
Oh, wow.
It is incredibly sensitive. During what is known as Sector 54 observations, which took place between July 22 and August 4, 2022, TESS captured the crucial light curves of this system.
2 weeks of just staring.
For basically 2 straight weeks, this satellite was staring unblinking at this point of light, recording the intricate, overlapping shadows these stars were casting on each other as they frantically orbited.
But wait, if they only watched it for 2 weeks, July 22 to August 4, how did they know about the fourth star? You just said the outer star takes 1,046 days to complete an orbit. It wouldn't even have made a dent in a 2-week observation window.
That is exactly why this discovery is such a triumph of observational astronomy. The TESS data was just the first thread they pulled. To a satellite, it initially just looks like a single point of light that is flickering in a very strange, seemingly chaotic pattern. The short 2-week window captured the frantic 51-day and multi-day orbits of the inner trio.
But not the big one.
Right. To find the fourth star and to confirm the exact nature of the inner three, the scientists had to combine the TESS photometry with archival data and high-resolution ground-based spectroscopy.
Okay, photometry is the moth in front of the headlight. What is spectroscopy?
Spectroscopy involves taking the light from that single blurry point and feeding it into a highly advanced prism, splitting it into its component colors, or a spectrum.
Like a rainbow.
Exactly. Every element in the universe absorbs light at very specific, unique wavelengths. By looking at the spectrum of a star, you see these dark bands called absorption lines, which act like a chemical barcode.
A barcode, okay.
But here is the magic trick. Because these stars are moving around each other, they are moving toward and away from Earth.
The Doppler effect, like a police siren changing pitch as it drives past you.
Precisely. As a star moves toward us in its orbit, its light waves are compressed, shifting its barcode slightly toward the blue end of the spectrum.
Oh, and it moves away.
As it swings around and moves away from us, the light waves stretch, shifting the barcode toward the red end. By meticulously tracking how these chemical barcodes split and shifted back and forth over time, the astronomers could measure the exact radial velocities of the stars.
They could see the gravitational tug-of-war encoded in the light itself?
They could.
That is staggering. So they aren't just looking at a shadow, they are looking at the color of the light, stretching and squishing, and using that to calculate the mass and speed of bodies they can't even see.
Exactly. By combining the minute variations in the photometric light curves with the shifting barcodes of the spectroscopic data, they were able to mathematically untangle the overlapping signals.
That's brilliant.
They could discern 4 completely separate, distinct gravitational signatures, and they could directly measure their individual temperatures, their specific physical sizes, and their masses.
This marks a massive milestone in the field, doesn't it? I mean, untangling 4 distinct signals from one dot of light.
It is a landmark achievement. This marks the very first time a 3+1 type quadruple star system has achieved direct spectroscopic detection of all 4 of its constituent stars.
The very first time.
Yes. They didn't just infer the presence of a 4th star based on a slight gravitational wobble. They chemically and visually confirmed the unique light signature of every single one of them.
Wow.
They tracked the slow 3-year red and blue shift of the outer star alongside the frantic daily shifts of the inner 3.
Okay, so you've got these 4 massive bodies packed together. They've measured them. They've confirmed them. My immediate thought is, how do they even get there?
That's the million-dollar question.
Did they just randomly capture each other while flying through the galaxy? Or is there a specific origin story? Because getting 3 stars inside Mercury's orbit feels like trying to parallel park a semi-truck in a compact space.
To answer that, the researchers had to look at the geometry of the system, and they found a massive clue hidden in the way these stars align.
Geometry.
Yes, the entire quadruple system, all 4 stars, sits on a relatively flat inclination.
Flat.
If you were to draw a line through their respective orbital planes, they mostly exist on the same 2-dimensional plane. It is like a cosmic dinner plate.
And why is that a clue? Doesn't everything in space just sort of orbit in circles anyway?
Not at all. Space is 3-dimensional. If you had a scenario where a binary star system was flying through space and just happened to gravitationally capture 2 other passing stars over millions of years, their orbits would be completely wild.
Oh, I see.
They would be coming in at all sorts of random tilted angles like a chaotic swarm of bees.
So they wouldn't line up neatly.
Exactly. The fact that they are flat is incredibly significant. In astrophysics, this kind of geometric alignment is considered primordial.
Primordial, meaning it's a leftover artifact from the very beginning.
Yes. The flatness is a residual physical fingerprint from the very process that formed the entire system from the ground up. It tells us definitively that this system did not form by random chance captures. All 4 of these stars were born simultaneously from the exact same, originally flat disk of gas and dust.
Okay, so take me back to the beginning. What does that birth actually look like? Are we talking about a stellar nursery, one of those giant glowing clouds you see in Hubble images?
Exactly that. Imagine a massive, sprawling molecular cloud, mostly hydrogen and helium gas, mixed with cosmic dust, sitting in the deep freeze of interstellar space.
Got it.
Something triggers a collapse in a pocket of this cloud, maybe a shock wave from a distant supernova. As the gas begins to collapse inward under its own gravity, it starts to spin.
Just naturally start spinning.
Yes, and as it spins faster, conservation of angular momentum forces it to flatten out into a disk, much like a ball of pizza dough flattening out as a chef spins it in the air.
Okay, so you have this giant spinning pizza dough made of hydrogen. How do you get 4 distinct stars out of it instead of just one giant superstar in the middle?
The mechanism at play here involves a very specific, complex physical process known as sequential fragmentation.
Sequential fragmentation.
As this massive disk spins, it begins to cool. When gas cools, it loses the thermal pressure that was fighting against gravity. Gravity starts to win, pulling clumps of material together within the disk.
Okay, so it gets clumpy.
Exactly. If the disk is massive enough and if it cools rapidly enough, it becomes gravitationally unstable. Instead of all the material rushing smoothly into the center to form one giant star, the disk essentially breaks apart in stages. It fragments sequentially.
So the pizza dough gets lumpy, and those lumps start pulling in more dough until they ignite.
A very apt way to put it. The central, densest part of the core might form the innermost binary pair first.
That's star AA and its partner.
Right. But there is still a massive, heavy spinning disk of material left rotating around them, so that remaining disk fragments again, gathering enough mass to collapse and ignite the 3rd star.
The angry hornet.
Yes. And then, much further out in the cooler, less dense reaches of the disk, a final fragment collapses to form that 4th sun-like star.
That explains why they're all on the same flat plane, because the dough was already flat before it got lumpy.
Exactly. The initial angular momentum of the primordial disk dictates the orbital planes of everything that forms out of it.
That makes perfect sense.
And what is also fascinating here is that the physics of sequential fragmentation naturally favors the creation of binary or multiple star components that have nearly equal mass. This perfectly explains why the inner three stars are all relatively massive and hot, similar in scale to one another compared to the outer star.
But hold on, back up. That makes zero sense to me when we look at their current locations.
Why is that?
If they formed from different rings of a spinning disk, the center, a middle ring, and an outer ring, they should be further apart. If the inner three stars currently fit inside Mercury's orbit, how do they get crammed in there? They couldn't have formed that close together initially, could they? There wouldn't have been enough raw gas in such a tiny spatial volume to build three massive stars.
You have hit on the exact paradox that astronomers had to solve. You are entirely correct.
Oh, I am.
Yes. They could not have formed in their current, incredibly compact configuration. The physical volume within Mercury's orbit simply cannot hold enough primordial gas to birth three stars of that mass. They had to have formed much further out in the disk and then moved inward.
Moved inward?
Yes. And this is where a concept called disk-driven migration comes into play.
Disk-driven migration. So they literally surfed the disk inward. How does a star migrate? It weighs millions of times more than the Earth. It doesn't just casually drift.
It requires immense forces, and those forces are supplied by the disk itself. Even after the stellar cores have fully formed and ignited, they aren't orbiting in a clean vacuum yet.
Because there's still all that leftover gas.
They are still embedded deep inside the remnants of that massive primordial disk of gas and dust. As the young, massive stars move through this dense material, they experience friction.
Oh, wow. Friction in space.
Furthermore, their immense gravity creates wakes in the gas disk, much like a boat creating a wake in water. The gravitational interaction between the mass of the stars and the dense spiral density waves they whip up in the surrounding disk actually leaches orbital energy away from the stars.
It's like trying to run through waist-deep water instead of running on a track. The drag slows you down, and in orbital mechanics, when you lose energy and slow down, you don't just stop in place, you lose altitude, you fall inward toward the center of gravity.
Precisely. The conservation of orbital energy is unforgiving. As the disk strips momentum from the stars, the dynamics physically force these inner stars to migrate closer and closer to the center, shrinking their orbits over thousands and millions of years.
That is terrifying and amazing.
This continuous inward pull, driven by the friction and gravitational drag of the disk, is what ultimately resulted in the incredibly compact, tightly wound inner subsystem we are looking at today.
So they formed far apart. The gas dragged them inward until they were practically touching. And then what? Why didn't they just keep migrating until they crashed into each other and merged into a settled star?
Because eventually the disk runs out of material. As the stars burn hotter and brighter, they generate intense stellar winds and radiation pressure. This pressure begins to physically blow the remaining gas and dust out of the system.
They clear their own neighborhood.
Exactly. Additionally, whatever gas isn't blown away is actively accreted or eaten by the stars themselves. Once that primordial disk material was finally cleared away, the friction disappeared. The migration stopped. The stars were effectively locked into their current, incredibly tight configuration.
The water drained from the pool, so the drag stopped, which naturally leads anyone listening to wonder about the safety of this setup right now. You just described an origin story that sounds like a near-miss catastrophe.
It does.
You have three massive, ultra-hot stars crammed into a space smaller than Mercury's orbit, whipping around each other every few days, with a fourth star acting as a giant gravitational boundary. Are they going to crash into each other tomorrow?
The good news is, no, not tomorrow, and not for a very long time. Despite the incredibly close quarters and the sheer kinetic energy involved, the current architecture of TICA 120362137 is remarkably stable.
That is surprising.
The researchers ran extensive N-body gravitational simulations and determined that these orbits are expected to remain stable throughout the entire main sequence lifetime of these stars.
I hear that term a lot in astronomy. Main sequence. What does that actually mean for a star? Is it like a star's prime working years?
That is a perfect way to think about it. The main sequence is the prime of a star's life. It is the period during which a star is actively and consistently fusing hydrogen into helium in its core.
Okay, fusion.
This fusion process releases immense amounts of energy, creating an outward thermal pressure. This outward pressure perfectly balances the inward pull of the star's own massive gravity. This state of balance is called hydrostatic equilibrium.
So as long as the engine is running and pushing outward, the star doesn't collapse.
Correct. For stars like the massive ones in the inner trio, this main sequence phase can last for millions or billions of years, depending on their exact mass.
Do bigger stars live longer?
Actually, the opposite. Generally, the more massive a star, the faster it burns through its hydrogen fuel, resulting in a shorter life.
Oh, interesting. Fast and Furious.
Exactly. But as long as they remain in the stable hydrogen burning phase, their physical sizes and their gravitational interactions, while complex and frenetic, will maintain this delicate balance. The 3+1 dance will continue uninterrupted.
And there is always a massive cosmic... But when we were talking about stellar dynamics on a timeline of billions of years, this delicate dance absolutely cannot last forever, can it? Because the fuel eventually runs out.
It does. When we look to the deep future of TIC-1 120362137, the simulations of its stellar dynamics show a very dramatic, inevitable conclusion.
I knew it.
Eventually, these stars will exhaust the hydrogen fuel in their cores. When that happens, the hydrostatic equilibrium is broken.
Because the engine stops pushing out.
Yes. The outward pressure drops, and gravity temporarily wins, crushing the core inward. This crushing actually heats the core up so much that it triggers fusion in the outer layers of the star.
And when a star starts burning its outer layers, it swells up.
Yeah.
It becomes a red giant.
Exactly. The stars will expand massively in volume. And this is where the extreme compactness of TEC 120362137 becomes its doom.
Oh, no. Because they are so close.
Remember, they are currently sitting inside a boundary smaller than Mercury's orbit. If even one of those massive inner stars expands into a red giant, it will physically swell past its own gravitational boundary, a limit known as the Roche lobe.
The Roche lobe. So it swells so big that its own gravity can't hold on to its outer layers anymore.
Precisely. The outer layers of the swelling star will literally be pulled off by the intense gravity of its incredibly close neighbor.
It just strips it bare.
This initiates a process called mass transfer. Star A starts dumping millions of tons of superheated plasma onto Star B. This drastically alters the mass of both stars, which in turn drastically alters their gravitational pull, which destabilizes their previously perfect orbits.
The intricate salsa dance turns into a violent mosh pit.
It becomes incredibly chaotic. The simulations indicate that the system will ultimately undergo a catastrophic collapse. The tightest pair in the center will likely interact first, transferring mass and altering their orbits, which will inevitably destabilize the third inner star.
So there's no escaping it for them.
None. The inescapable destiny for the inner three stars is that they will merge entirely.
Merge.
We are talking about an incomprehensibly violent cosmic pileup where three massive blazing stars collide, spiral into one another, and consume each other in a massive release of energy.
That would be a sight to see.
Yeah.
A luminous red nova, just three suns ripping each other apart until there is only one left.
It would be spectacular.
And what happens after the dust settles from that apocalyptic merger? You've got this one massive Frankenstein star sitting in the middle and the little sun-like star still dutifully orbiting on the outside. Does the Frankenstein star just live happily ever after?
It does not.
Of course not.
Yeah. The massive singular entity created by the collision will have a very turbulent, short lifespan. It will eventually burn out the last of its usable nuclear fuel. Without fusion to prop it up, it will shed its outer layers into a beautiful planetary nebula, leaving behind only its dead, hyperdense core.
So it shrinks down.
Yes. The final result of this entire spectacular inner three-star system will be a single white dwarf.
A white dwarf, just to ground it for everyone, a white dwarf is essentially a star that has the mass of our sun, but it has been crushed down by gravity until it is roughly the physical size of the Earth. It's just a glowing ember of incredibly dense matter.
Supported entirely by a quantum mechanical phenomenon called electron degeneracy pressure, where the electrons literally refuse to be squeezed any closer together.
It's just so dense.
It is dead. No fusion is happening. It is just slowly cooling in the dark.
And what about the fourth star? The little sun-like soloist out on the edge.
Eventually, billions of years later, that outer fourth star will run out of hydrogen, go through its own red giant phase, shed its layers, and also become a white dwarf.
So, the grand finale. The end of the movie for TOT 120362137.
Yes.
It goes from a massive, sprawling disk of primordial gas to a blazing, frantic quadruple star system packed into an impossible space, down to two quiet, impossibly dense, cooling white dwarf cinders just orbiting each other in the dark.
A binary white dwarf system. It is a profound and sobering life cycle. And this inevitable dramatic fate is precisely why the continued monitoring of TAC 120362137 is so vital to the scientific community.
Because we are essentially trying to build a timeline from a single photograph, right?
That is the challenge of astronomy.
Tracking this system and hopefully finding and monitoring any future quadruple systems out there is essential for astronomers. They're trying to crack the code of how these exotic rare systems evolve dynamically over billions of years.
Exactly.
We're currently just looking at one single microscopic snapshot in a cosmic movie that takes eons to play out.
Yes, and by gathering high-precision photometric and spectroscopic data on systems like this, we can feed real-world numbers into our supercomputers.
To predict the future.
To predict the future and understand the past. We can refine our N-body simulations and better understand the hidden gravitational rules that govern the universe. It allows us to test our theories of sequential fragmentation, disk-driven migration, and stellar evolution in extreme boundary-pushing environments.
It really is a staggering reality to visualize. 4 massive stars occupying the same physical space as our peaceful inner solar system. We have this quiet little neighborhood with our one sun, and somewhere out there, 4 stars are locked in a gravitational cage match that is destined to end in a massive merger, leaving behind only glowing embers.
It is a lot to take in.
It makes you look at the night sky completely differently.
It should. It leaves you with a thought worth mulling over long after you hear this.
What's that?
If a system this intensely complex, this tightly packed, and this chaotic can somehow maintain a stable, intricate gravitational dance for billions of years before its inevitable collapse, what does that say about the unseen, delicate balances keeping our own seemingly empty solar system in check?
Oh, that's a good point.
Our local neighborhood feels incredibly calm, but it is governed by the exact same unforgiving, chaotic forces of orbital mechanics.
It makes you wonder, what other fortuitous and chaotic cosmic dances are hiding just behind a single point of light in your night sky, just waiting for us to decipher their rhythm?